Hello and a very warm welcome to my video on perfect numbers. What are perfect numbers? Well, a perfect number equals the sum of its smaller factors. Take for example 6. 6 has smaller factors 1, 2 and 3, and when we add them together, 1 plus 2 plus 3, we get 6. Then we can do the same for 28. 28 has smaller factors 1, 2, 4, 7 and 14, and they added together give 28. The first 5 known perfect numbers are 6, 28, 496, 8,128, 33,550,336. And then the gaps get bigger and bigger as we go towards infinity. Now, in about 300 BC, Euclid showed that if p is prime, then 2 to the power of p minus 1 times 2 to the power of p minus 1, where p minus 1 is the exponent here on the second term. So Euclid showed that this is a way or a formula we can use to find perfect numbers. So we plug in a p and we can check if it's perfect, but it might not be perfect. But what it does allow us to do is that if p is not prime, then the number will not be perfect. So it doesn't work for every p. So take 6 for example. We have 6 is equal to 2 squared minus 1 times 2 to the power of 2 minus 1, which is 3 times 2. And you'll notice here that p is equal to 2 in this formula when we're working out what 6 is. So I've written p equals, and then I've put in a little brackets 2 above 6. For 28 it will be 3, p will be 3. For 496 p will be 5. 28 is equal to 2 to the 3 minus 1 times 2 to the power of 3 minus 1. You can check that yourself. So this expression has two terms. One of them will be odd, one of them will be even. This will always be odd because 2 to the power of something is even, minus 1 is odd, and 2 to the power of something is even. So odd times even. So 3 times 2, 7 times 4, you can see odd, even, odd, even. A quick counter example, if we let p equal 4, 4 is not prime, 4 is composite, but we can quickly see that 2 to the 4 minus 1 is 15 times 2 to the 4 minus 1 is 8. 15 times 8 is 120. If you add the smaller factors of 120, you will not get 120. This is not perfect. But you don't need to do that. You can show that it will not be perfect based on the fact that 4 is not prime. So later on, Euler proved that all even perfect numbers are of this form. So all even perfect numbers take this form. And then put all that work together that Euclid did at the beginning and then Euler, so it then becomes the Euclid-Euler theorem. Now it's not known whether there are any odd perfect numbers. That's an open problem. If anybody can prove that, I'll give you $1,000. Find me the first odd perfect number and I'll give you $1,000 guaranteed. And another open problem is, are there infinitely many perfect numbers, odd or even? If anybody can prove that, I will also give you $1,000. No, in fact, I'll give you $2,000 because I think that would be more difficult to prove. But they're both very difficult to prove. I would say they're almost equally difficult to prove. So, yeah, if you've got a bit of spare time and you think you can give it a shot, go for it. I wouldn't spend too much time on it, however, because they're extremely difficult. So that's a brief introduction to perfect numbers. Hopefully I will have a few more videos on perfect numbers in the future, going into some more detail and some of the technical stuff. But I just wanted to quickly show you that, just so you can understand what it's all about. So I hope you enjoyed the video. If you did, please like, share and subscribe, and I'll see you on the next video.